So yesterday we did some work showing how electrons actually move to form ionic compounds and kind of why their formulas are the way they are. So today we're going to kind of formalize that, put it into some notes and get some rules for naming and for translating those names into chemical formulas. Today we're just going to be talking about ionic compounds, and we're going to start by talking about the simplest class of ionic compounds, which are binary compounds. Binary, there's a word in there that should be a clue. Bi means two, like a binary star is two stars that orbit each other. So a binary compound is one which only has two elements. Full stop. If it has more than two elements, it's not a binary compound. So here's a few examples. This first one has just sodium and chlorine, aluminum and oxygen and nothing else. And the last one is sodium and oxygen, nothing else. These are all ionic compounds. And here's a really key thing that you want to make a big note of. We can always tell that something is ionic when it has a metal and a non-metal. Because remember, metals are the elements which lose electrons, and they give those electrons to a non-metal. So metals lose electrons, become cations, positive ions. Non-metals pick up those electrons and become anions, negative ions. And then those positive and negative ions are attracted to each other, and we form a compound like our KBr. Ionic compounds are often called salts. So yeah, the stuff on your table is NaCl. It is a salt. It is in fact table salt. But not all salts are table salt. We would not be very tasty if we were eating aluminum oxide. So let's think about how we name these. And luckily, it's really pretty simple. It's a two-word name. The first word is the name of the metal. You don't do anything to it. You just write down the name of the metal. So look at the periodic table, find the element, write it down. The second word does get a change. For the anion in this compound, we use the root of the nonmetal with the IDE suffix. So if you've heard table salt, well, that's NaCl, and the name of that is sodium chloride. We take the chlorine and we make it chloride to show that it is the anion. So if I look at the second one here, the first word would just be aluminum. The second word would take the root of oxygen, the ox, and change the ending to ide. So that would be aluminum oxide. And the last one here would be, first word is just the metal, so sodium. And again, we take the root of that nonmetal with the ide suffix, so that's just sodium oxide. Now, when we talk about molecular compounds, we'll see that they have similar rules, but they have some pretty different little things in there. So when something is ionic, we have to use these different rules. If the metal is a transition metal, this is why we have not been drawing Lewis structures and not been predicting the charges on the transition metals. Transition metals oftentimes are able to make more than one different ion. And so we need to have a way to say which of the ions we're talking about. In order to do that, we actually include that information in the name. We use it with a Roman numeral. Like, for example, you might see a 3 in Roman numerals in the middle of a name. So for example here, titanium oxide, well, titanium can make a +2 ion and a +4 ion. And we'll see in a little bit that the formulas would be very different if it was +2 or +4. So we need to say which one it is. This is titanium 4 oxide. And so to distinguish between the two of them, we put that 4 in the middle of the name. The key thing when we are thinking about writing formulas for binary compounds is that in order for the compound to exist on the beautiful green earth, it must be a neutral molecule. Nature is very into balance. So all of my positive charges must be balanced out by negative charges. If I ever wander by your paper and say, make something that exists, it's a hint to start checking your charges. So let's use this balance information to find the formula of potassium sulfide. Well, the name tells me that the metal in here must obviously be potassium, and sulfide, the sulf is sulfur that's been changed into sulfide. So we've got potassium and sulfur in this compound. So one way we could start is by thinking about those Lewis dot diagrams. Potassium is a very simple Lewis dot diagram. It's in group 1A, so it just has one valence electron. Sulfur is in group 6A, so it would have 6 valence electrons. That means we would go around one on each side to do the first 4, and then pair up 2 of them, so we get a total of 6. So these are our neutral elements. And remember, when we are trying to make ions, the idea is octets. We either want to lose our extra electrons to get back to an octet, or we want to gain electrons to fill in our empty spots. And you can see on sulfur, there's those 2 empty spots, one on the bottom where there's 1 unpaired electron, and one on the left of the sulfur where there's 1 unpaired electron. So let's think about how we can balance this out. That potassium is going to lose 1 electron and form the potassium ion, K+. That electron has to go somewhere, and there's a great spot for it right there on the left side of that sulfur. Pairs it up. But there's still a spot on the bottom which is unfilled. K+ is great, but S- is not going to help us out. We don't have a full low energy octet here. So what we really need to do is find another potassium ion. We can't take any more electrons from the potassium ion we just formed. We're going to have to make another one from another potassium atom. So you see I brought one in on the right here, and then it will lose its valence electron, form another K+ ion, and allow that electron to fill in the empty spot on the sulfur. So when we finish this, we end up with a neutral molecule, 2 positive charges from 2 potassium ions, and 2 negative charges from that one S2-. So I'm going to say it a lot. In order for something to exist on the pretty green earth, we need our positive charges to balance our negative charges. A compound that actually exists is always going to be neutral overall. It's going to have a net charge of 0. All the pluses get canceled out with minuses. So now I know this ratio. I need to go ahead and make that into a formula. And so I'm going to write that using subscripts, the small numbers on the bottom. Think about when you've seen formulas like H2O or C6H12O6 in biology. So this formula has 2 potassium ions, and we're going to show that by using the 2 subscript on the K, K2S. So let's think about another example. Let's think about something like barium oxide. Let's try to find the formula for it. Well, this is obviously ionic because it's a metal, barium, with a non-metal, oxygen. So let's think about what would the charges be on these ions. So take a look at your periodic table and find the charge on a barium ion. And I'll give you a couple seconds to pause and do that. Okay, so barium is in group 2, so it's going to be a +2 cation. We also need to find the charge on oxide. So we give you a few minutes to pause and find that on your periodic table and get the charge on the oxide. So you should have found the oxygen is element 8, has 8 electrons, so it would gain 2 electrons to make a -2 anion, so that it now has 10 electrons, isoelectronic with neon. Well, remember, we need to make this something that exists. Those charges have to cancel out. So what ratio of barium and oxygen leaves us with balanced out charges? That's pretty simple. 1 plus 2, 1 minus 2, that's 0. Plus 2 minus 2. So this is a pretty simple compound. It's just BaO. 1 barium plus 2 cancels out 1 oxygen minus 2. So I'll give you a little shortcut. That's really a very handy rule, but you can't use it while turning off your brains. One possible way to get the formula of a binary ionic compound is what we like to call the crisscross rule. We find the charges on the ions. So for example, we know potassium would lose 1 electron and become the K+ ion. We know sulfur gains 2 electrons and becomes the sulfur 2- ion. Then we're going to crisscross applesauce. We're going to take the number and drop it down across the compound to make the subscript on the formula. So the 1 on the potassium would go down and be the subscript on sulfur. So we don't usually put a 1 subscript in because it's kind of redundant. The 2 charge on sulfur is going to crisscross down to be the subscript on potassium, which gives us a formula of K2S. Hopefully that looks familiar because we just did it a few minutes ago. So you see this rule got us the same answer as the K2S we got while thinking about electron movement and our Lewis dot structure. The thing is, anytime I'm making a formula, I want to make sure that I always reduce my subscripts to the lowest possible values. So when I say don't crisscross with your brains off, I mean something like barium oxide. I've seen it lots of times where people will crisscross that 2 down from the 2+ and say, oh, that's Ba2O2. Well, that's not in lowest terms. Ba2O2 is nothing more than just barium oxide, BaO. So if you use the crisscross rule, make sure that you look at your subscripts and you check to see if there's any way to simplify them to get the compound into its lowest possible terms. Just like math class, you want to make sure you turn things in the simplest possible way. So that's binary nomenclature using predictable representative elements in the S and the P block. So in our next video, we'll talk a little more about doing that with transition metals.